Hello everyone. So this is the original research paper on generative adversarial networks, popularly known as GAN. So this paper is written by Ian J. Goodfellow. He's also called father of GAN, and he has also written a very good book called Deep Learning. In that there is one chapter called generative modeling. You can refer to that book also. So what exactly is adversarial model? So it's a two-player competing against each other, as name suggests. In more technical terms, it's training a model in worst case scenario with input chosen by an adversary. So in terms of GAN, two players are neural networks, discriminator and generator, and they are competing against each other. Ultimate goal of generator is to fool discriminator by generating realistic data. Goal of discriminator is to identify real data. So it's a binary classification model. Worst case input for discriminator is produced by generator, and GAN is used for, we all know, image data, but it can be used for video, audio, symbols, etc. So this is the structure of the paper: introduction, adversarial network, then theory, experiment, and advantages, disadvantages. Well, we have discussed this abstract over there. So just some key points. So uses min-max two-player game. We'll get to know this. No Markov chain or approximate inference, and it uses only backpropagation for training. So introduction. So this paper was written in 2014. During that time, the most successful models were discriminative model, which used backpropagation, dropout, and PLUs. So some motivation. This GAN has taken from this discriminative modeling. To explain GAN, they have used a very good example over here. And if you have watched Hindi series called Fuzzy, you can also relate. So let's suppose there are two teams. One is a counterfeiters and one is police. So police is trying to cash fake currency, and counterfeiters is trying to fool the police. So in this process, police is also becoming better at catching, and counterfeiters are trying to make currency by which they are able to fool the police. So their ultimate goal is to produce a fake currency which is undetectable, right? So that's what GAN is trying to do. So its ultimate goal is to produce data which is undetectable by the discriminator, but in the process, discriminator is also getting trained. So this is how it looks while training. Generator and discriminator both are being trained using backpropagation and dropout, but while running, only generator is executed with forward propagation. So related work. So there have been other models for generative data like Boltzmann machines, deep belief networks, autoencoders, generative stochastic networks. They have used different methods. Some have used backpropagation also, but Markovian chain, Monte Carlo, MLEs. You can refer to these also. Okay, so from here the interesting part starts. Adversarial network. So this is the diagram that I have built based on this research paper and other information. So there is a generator which is connected with discriminator. Input to generator is a random noise. Let's say its distribution is Pz of z. It will go through generator and it will generate an image Gz. Input to discriminator is generated image and input image. So input image is the original image from the data set. Parameter of generator is theta g. Parameter of discriminator is theta d. So discriminator is trying to detect the images from data set as one, that is real. Discriminator is trying to make generated images 0, so that is it is trying to identify them as generated. So generator is trying to fool the discriminator, so it is trying to generate an image for which discriminator identifies it as real. So this is the objective function of min-max again. So this is nothing but a cross entropy function, normal cross entropy. So where there is one loss associated with discriminator unable to identify the real image, and another loss is associated with discriminator and unable to identify generated images. Now this is a theoretical discussion. So the loss of discriminator is minus V of D of G, and loss of generator is minus of loss of discriminator, because it is trying to do the opposite. It is trying to fool the discriminator. So this is the objective function we'll try to solve in this one. So where the loss of discriminator or the cost function associated with discriminator is V of D of G, where we are trying to maximize D, and cost associated with generator is J2. So only this term where it is trying to fool the discriminator, and there we are trying to minimize G. And there is another version, so this is more practical. I think in this research paper also it is mentioned, but what algorithm they have solved, they have used min-max game. But there is a more practical version called non-saturating game. So in non-saturating game, only difference is the cost function of generator has changed. Here, the cost function of generator, instead of minimizing 1 minus d g of z, we are maximizing log of t of g of z. And the purpose of this is it is giving more gradient. If you plot log of y compared to log 1 minus y, log of y will have more gradient as compared to log 1 minus y. So this is how this learning will look. So see, this is very good example. Here this is the data set This is the generated data set, and this is a discriminator. So it is able to identify real from fake very easily in the beginning. Then slowly generated data is trying to mimic this actual data, and discriminator is also able to identify significantly well between generated and fake. Finally, so this is the optimal condition where this generated data will become equal to our distributed data. In that case, discriminator is unable to identify generated and discriminated, so it will give a constant output of 1 by 2. So this all we'll learn in this theoretical section now. Yeah, so global optimum condition is where PG is equal to P data. So distribution of generator is equal to distribution of the input data set. So now coming to algorithm. So this is a mini batch stochastic gradient algorithm, and this is basically a two-step algorithm. So in one step, so this is the min-max function that we already discussed. So in first step, we are maximizing discriminator for discriminator function, right? So this is maximizing, we are doing ascending. In second step, we are minimizing generator function. So since it's a minimum, we are doing descending stochastic gradient. So we will alternate between discriminator optimization and generator optimization. Well, they say that case steps also you can do, but generally with this one to one. Yeah, so with this we already discussed. So global optimality. So it will be achieved when PG becomes equal to P data. And then what will happen at that point? So the optimal discriminator will become P data X by P data X plus PGX, right, for a fixed G. And this is all the proof is given over here. So at global minimum condition, PG will become equal to P data, and at that time our cost function will become minus log 4, right? Because we already discussed that discriminator will give 1 by 2, 1 by 2 output everywhere. So this is another derivation. So you can go through this derivation. There's like 8-10 pages of derivation. But the final thing is that you look at this expression. So it's saying that CG is equal to minus log 4 KL divergence. And in terms of Jensen-Shannon divergence, this is cost function is minus log 4 2 into JSD. So you will find this derivation somewhere, and it is 8 to 10 pages of derivation. And yeah, this is convergence. So what they are saying that if there is enough capacity, enough data, enough steps in the algorithm, gradient is not vanishing, then PG will converge to P data. So this GAN has been run on MNIST data, TFT data, Cypher 10. All these are popular data set. So generators have used ReLU, sigmoid activation, and discriminator has used maxed out activation. Dropout was applied in training the discriminator. So this is the example of this generated data they have shown. So they have shown this is the training set, and this is the data which is generated. So in all of these four images, the final column is generated data, and this signifies that this is not a copied data. See, this is a generated data, right? It's not copied. This is another important achievement of GAN. Well, finally, so advantages and disadvantages of GAN. So let's go into advantages first. So it does not use Markov chain. Well, it has been repeated so many times. So let me tell you what this paper refers to. So this paper tells that because Markov chain is one, it is long calculation. Second, it is not able to learn sharp images properly. So that's why Markov chain is at disadvantages. It only uses back propagation. Inputs are not copied directly, that we already saw in the diagram previously, and sharp, less sharp, blurry, all kind of distributions can be learned in this one. So problems, so there are two major problems. One is non-convergent. So the distribution of generator, right, PGX, there is no explicit distribution for that, and discriminator has to synchronize with it. Second is Helvetica scenario or mode collapse. So Helvetica scenario is a funny reference from All You Need to Know show or something like that. So what does this mode collapse or Helvetica scenario mean is that if we train G too much, right? So what G will do is G will collapse to a point where it has not learned the distribution, but it is able to fool the discriminator. So that's why we saw in the beginning, right, that G and D should be alternatively trained to avoid this mode collapse. Well, in conclusion, they have given conditional GAN models are used, which we will see in one of our upcoming videos. Then another important thing is semi-supervised learning could be used to improve the performance and efficiency improvement. So in terms of training, it could be accelerated. Thank you so much for watching this video. Please subscribe and like if you like the video. Post your questions in the comment, and also post suggestions for new video or next research paper in the comment. Thank you so much.